This is the design of a campus motor fleet for the FAA Technical Center to meet Executive Order 13514, as done by Shane Armstrong, Caleb Ben, Alicia Kubokawa, and Kelly Prim. This project looks at the replacement of the FAA's motor fleet with alternatively fueled vehicles in order to reduce greenhouse gas emissions as directed by the Executive Order. The President of the United States has issued the following two directives in an effort to encourage green initiatives. The parts of the executive order that directly impacted our project were its requirements on petroleum reduction, greenhouse gas emission reduction, and fleet size optimization. The presidential memorandum is relevant in that it supplements the executive order and emphasizes the use of alternatively fueled vehicles. Federal Aviation Administration, being a part of the Department of Transportation and an entity within the government, is subject to the executive order and presidential memorandum. It is in charge of the national airspace and has many facilities and centers across the country. This project was focused on the William J. Hughes Technical Center located near Atlantic City, which is predominantly used for engineering, research, development, and testing. The map addresses the issue that the current FAA vehicle fleet at the Technical Center is not on track to meet the EO requirements enforced by the DOT. If nothing is changed and the fleets remain as they are, there is a projected 6% increase in carbon dioxide emissions by the year 2020, represented by the blue line. The green line is the reduced CO2 emission goal as derived from the EO petroleum usage reduction requirements and current CO2 emission contributions of GHG. Here are the stakeholders affected in this project. As you can see, they are color-coded to indicate their involvement, with yellow indicating implementers such as the FAA and labor unions, blue indicating oversight groups such as the Department of Transportation and several steering committees, and gray indicating external stakeholders such as the White House and local residents. The primary stakeholders are the FAA management, aviation logistics organization, fleet managers, and the vehicle users. The problem facing the FAA is that they need to appease their oversight groups and follow the EO, which calls for a 12.3% reduction in greenhouse gas emissions by the year 2020, while meeting current campus demand and staying within the current budget. That 12.3% was translated into 13% CO2 emissions for the purpose of this project and was calculated due to the fact that 95 to 99% of all greenhouse gas emissions emitted by petroleum-fueled vehicles are CO2. Thus, there is a need for a system which can calculate GHG emissions of alternatively fueled inventories, replace inventory with alternatively fueled vehicles, and provide total life cycle cost estimates. These are the requirements set for the system as determined from conversations with our stakeholders, which include the importance of providing an equal or reduced inventory, reduction in CO2 emissions, and making sure vehicles proposed will be feasible and current, and future travel demand will be met, all while staying within budget. Here are the alternatives, which were chosen based on our requirements and stakeholders' needs. The current fleet is almost completely composed of petroleum-fueled vehicles and produces a significant amount of carbon dioxide emissions when compared to greener alternatives. Compressed natural gas vehicles are similar to standard gasoline vehicles, but contribute 30% less CO2 emissions, while both neighborhood electric vehicles and low-speed electric vehicles produce zero direct CO2 emissions. Even though they are powered the same, it should be noted that low-speed electric vehicles cannot go on the road and generally have a max speed of 25 miles per hour, whereas neighborhood electric vehicles can hit a max of 35 miles per hour and go on marked roads. Here's a black box diagram of the two models used in the simulation, the first of which being a demand model, which takes in Excel sheets with different vehicle inventories as well as campus attributes and outputs, average monthly vehicle mileages, which are then fed into the lifecycle cost model along with energy and maintenance costs, which then outputs total lifecycle costs for each inventory. One of the campus attributes important in the creation of our demand model was the grid in which charge codes for each division were assigned origin squares. In the demand model, service events would occur starting at the charge code origin, and the destination was determined on the probability of the highlighted squares in the grid. Here's a verification of our demand model. You can see an example of historic data compared to our demand model mileage outputs. The longer tail on the right-hand side of the historic data can be explained by our scope in which we excluded off-campus trips, emergency, and heavy-duty vehicles. Now that we have covered the demand model, we will be moving on to the second model of the deterministic and stochastic lifecycle costs. Here are the equations behind the different costs used to calculate the total lifecycle costs, composed of several different costs such as that of acquisition infrastructure. The maintenance costs were separated into preventative and corrective costs, and energy consumption costs were calculated using a geometric Brownian motion with drift. Corrective maintenance was modeled with log normal distributions using historical data from George Mason University's own motor fleet. As can be seen in the top left, CNG inventories had a much higher corrective maintenance cost per month than LSEVs, which can be seen in the chart in the bottom right. Of the energy costs, CNG was found to be the cheapest alternative cost per gallon equivalent, but had the highest volatility and expected cost increase. Electricity was the most expensive alternative, but had the least volatility and the lowest expected increase in price. Here you can see the results of our geometric Brownian motion with drift. The top left shows 100 trials over a year for gasoline. The variance increases as time goes on. The bottom right shows a more simplified version in which only 6 trials are shown. The forecasted prices tend towards an expected value, but there are still outliers due to the volatility of the model. Based on our results, all of the energy alternatives met the carbon dioxide reduction goal to varying degrees. A fleet composed of all CNGs would show a 46% reduction, and LSEVs and NEVs showed 89% and 88% reductions respectively. The CNG inventory had the highest TLCC, and LSEVs had the lowest based on our 6-year projection. This is a breakdown of all the costs that went into the total life cycle costs. While petroleum vehicles had the lowest acquisition and corrective maintenance costs, their energy prices were the highest. It should also be noted that the acquisition costs would accrue over time as petroleum vehicles are leased, while NEVs and LSEVs would be purchased outright. CNGs had the largest corrective maintenance costs, proving too expensive to be feasible, and the LSEVs and NEVs had the lowest energy costs. We also conducted a sensitivity analysis in which we removed vehicles from charge codes based on their utilization information, meaning that charge codes with vehicles that were underutilized based on our demand model were removed from the inventory and rerun to ensure that our demand could still be met. We tested those inventories against our objective function based on the costs of underutilization, wasted labor, inventory size, and missed events. These criteria showed the impact from a cause versus value standpoint. Here are the results of each of the inventories tested in our sensitivity analysis. The status quo had the lowest costs. While reductions in vehicles from certain charge codes minimized underutilization costs, the increased cost of average and standard deviation waiting times outweighed any benefits from reducing the costs. Here you can see our value hierarchy with weights based upon surveys completed by our stakeholders. These weights were used to evaluate all of our alternatives. The utility versus cost graph with the full inventory shows the LSEVs yielding the highest utility at the lowest cost, while the gasoline inventory has a low cost but the lowest utility. Here you can see the status quo inventory size of 42 compared to an inventory of 41 vehicles. While the smaller inventory yields lower costs, it also yields lower utility values. Similar to the previous slide, one can see the trend of the reduction in cost and utility incurred with the removal of inventory. As our goal was a 13% CO2 emission, which translates to 12.3% reduction in greenhouse gas emissions by the year 2020, as indicated in the executive order, all of our alternatives proved sufficient. Although it would be difficult to replace all vehicles at once, we suggest that in order to meet the EO by the year 2020, either 7 electric vehicles or 13 CNGVs be purchased. Financially speaking, LSEVs have lower 6-year costs than the current inventory and show a break-even point at 30 months, while CNGs require a much longer period of time before a return on investment is seen. It also shows that the inventory is capable of being optimized with further analysis, ensuring that the greatest factor being that of which vehicles are taken from each charge code. Inventory utilization does not directly correlate to queue size, waiting times, or missed events. Going forward, we recommend the implementation of a robust fleet management system which would record information such as trip volume, trip time, and trip purpose to improve tracking metrics. We also recommend replacing campus inventory with LSEVs and NEVs when budget allows and environment is accommodating. Thank you for listening to our presentation. We hope you enjoyed it.